this special edition of the Civil Brief program, where we are looking at developments in the design of earth-retaining structures. I'm Jane Wilcox. In this program, we will be talking to members of the Standards Committee, which have developed a new Australian standard on earth-retaining structures, about some of the major issues addressed by this standard. We will also be looking at the planning of adequate drainage provisions for retaining walls, an example of innovative reinforced backfill material, a presentation on segmental masonry retaining walls, and finally a brief look at a new pavement overlay being used in the USA called ultra-thin whitetopping. Earth-retaining structures may range from simple 1 metre high brick retaining walls or much higher retaining walls where the backfill may be reinforced either with steel strips or geotextiles. It's the soil backfill behind the retaining wall which produces the thrust on the wall, and it's the magnitude and direction of this thrust which is the chief concern in the analysis of earth-retaining structures. In determining that thrust, the classical theories of Rankine and Coulomb have been around for well over 100 years, and despite their simplifying assumptions, are still useful today. Also useful in determining the thrust are empirical results from tests, and engineering experience and judgment also plays a part. Once we've estimated the thrusts on the retaining wall, the next step is to ensure the structure has the strength to withstand these applied loads. For many years it has been common practice to use the total factor of safety approach when checking the overall stability of retaining structures. This seems to have worked quite well. Therefore, you may well ask, why is it necessary to come up with a new Australian standard on the subject? This new standard is the work of Committee CE32 and is based on the limit state design approach. Engineer Mark Sabolch interviews Committee Chairman Dr. Manfred Hausmann and Committee Member Rod Johnston.
Manfred, why was there a need for a reappraisal of the approach to the design of earth-retaining structures?
The basic need did arise from the introduction of many new soil reinforcing systems. And road authorities or other developers which had to choose between the conventional wall design and a reinforced soil wall design had to have a basis to compare their safety and long-term performance. And that's where the new standard is going to provide assistance, apart from also giving some good guidance in terms of proper design, proper drainage provisions and construction practice.
The new standard is based on limit state design concepts. Can you tell me why it was considered necessary to move away from the traditional total safety factor concept?
Well, structural engineers, of course, have been using limit state for some time. So as geotechnical engineers would just be following their lead. And there's a good argument in saying that the foundation or a retaining wall supporting a structure should be designed according to the same philosophy. But there are other factors which prompt us to adopt limit state design, like the Eurocode, which will be a very important document in the future of engineering, that also follows limit state design. But what prompted us initially, of course, is that reinforced soil walls have more variables involved in the design than an ordinary conventional wall. And limit state design concepts are ideally suited for that type of problem.
How does the limit state design relate to the old total factor of safety approach?
Well, in the total factor of safety approach, we simply had a factor of safety expressing the ratio of strength over load, that type of approach. It didn't differentiate the components of resistance, such as frictional strength or cohesion in the soil, and it assigned the same factor of safety to both components. However, in the limit state design, the design capacity has to be equal or larger than the design action effect. So in other words, the factored down resistance has to be equal or larger than the factored up loads. The limit state design criteria for serviceability can be formulated in the same way, so that the allowable deformation must be larger than the actual deformation under the specified loads.
Right. I understand that the material properties used in design are characteristic values. Just what are characteristic values?
Characteristic values are simply representative values for a material property. Now, they could be expressed in as a mean of available test results, or they could be, the characteristic value could be chosen as a 5th percentile value. Let's say a value which is exceeded by 95% of all test results. For soils, total factors of safeties were based on mean values of resistance and mean value of load and mean value of stress. Characteristic values for limit state design could be chosen the same way. However, in geotechnical engineering, we generally do not have enough values to apply statistical means of selecting a characteristic value. We could simply make a cautious estimate of the mean, partially based on experience, partially based on the information available. Statistically, we could actually try to define the desirable value by looking at the distribution of means of samples. And we could define the characteristic value as the 5th percentile value of the distribution of the means of samples with a limited number of test results. The standard does not give precise guidelines of how to determine this characteristic value. It would still be up to the judgment of the engineer to choose an appropriate value.
Thanks, Manfred. And now we turn to another member of the Standards Australia Committee, Consulting Engineer Rod Johnston, who's had long experience in the design of masonry retaining walls. Rod, on a practical level, how do we determine characteristic values for design purposes?
Well, the first step would be to make sure that each particular wall which has to be designed has the correct soil properties behind it. For example, you might be on a fairly large site which has got retaining walls around 3 sides of it. On one side you've got a particular soil acting on one wall, but on the other side of the site you might have a different soil acting. So you need to isolate those parts of the structures which have significantly different soil properties acting on them. The second step would be to make sure that you have the correct soil properties which are being determined. These are generally friction angles or cohesions, and you need to satisfy yourself that it's the mean value of these particular properties that you're designing for. Now, Manfred's already described how the standard permits you to estimate these mean values to provide a cautious estimate of the mean. The code is very flexible in this area. You could use statistical techniques described by Manfred. You could use a history of information which you already know about the particular site or similar sites. And obviously you'd have to back this up with site investigation and general engineering judgment.
On one side of the fundamental equation, S star refers to the design loads. What does the new code say about determining the load factors?
Well, the code recognises that the main structures which are involved here, the steel and the concrete and the masonry, are all going to be designed to Australian standards which derive their loadings from the Australian Loading Code, AS 1170. So in this standard we've tried to do the same thing. We've referred the load factors and the load combinations to Australian Standard AS 1170, and we've even reproduced that in one of the appendices. The sort of factors that we're talking about are 1.25 on dead loads, 1.5 on live loads. We've got allowance in there for earthquake and wind loads and the like. Now, there are some exceptions and some additions which we've made. For example, we have a 5 kPa live loading which we've suggested should be added to the top of walls as well. We've also adopted a 1.1 factor on liquid loads or hydrostatic loads, which is slightly different from the loading code. The other major difference is that we've also recognised that there are other structures which need to be designed to a completely different loading situation, perhaps roads or bridge structures, and we make reference to those in the standard so that designers can opt to use those as opposed to AS 1170 should they so require.
On the other side of the equation we have R star, or factored down strength. What does the code say about material reduction factors, and what are they based on?
The material reduction factors have to account for two quite separate situations. One is a reduction in soil properties, and this will affect not only the resistance of the soil to movement of the structures, but it will also affect the loads that those soils actually apply to the structures. And I'll come back to that in just a second. The second set of factors relate to the strengths of the materials themselves used to retain the structures, the geogrids and the like, to allow for corrosion, for deterioration, for reduction in strength over time and so on. Now, just returning to the soil properties, what we're suggesting in the standard is the tangent of the friction angles be reduced depending upon the reliability of the data available and also on the nature of the fill which is involved. This will have a dual effect. First of all, it will have the effect of increasing the loads on the structure, and secondly, it will have the effect of reducing the resistances that that soil is able to provide to movement of the structure. Now, an important consideration here is the reduction in friction angle combined with the load factor of 1.25 on dead loads, which includes soil weight. Those two factors combined will approach the AS 1170 recommendation of a global factor of 1.5 on earth loads. So it's important to understand that this 1.5 requirement from AS 1170 has been accounted for in two ways: a 1.25 load factor and a 0.8 to 0.9 reduction factor on the tangent of friction angle.
How does the designer select the right material reduction factor for the various retaining wall components?
Well, the standard gives default values which a designer can use if he doesn't have other more precise information. But I would suggest that designers seek from manufacturers test data which they would already have and use that information in their particular design. The important thing is to make sure that you end up with a realistic scenario for how the reinforcement is going to behave. You can make a big mistake by just plugging in the minimum values from the standard without any further consideration.
But numerically, where do the numbers in the code come from?
The values which are in there are worst case scenarios for particular materials. If you like, they're the lower bound or the worst possible situation that could arise.
Thank you, Rod. Thank you, Manfred.
Thank you.
Some textbooks tell us that the design of adequate drainage provisions is just as important as the correct evaluation of earth pressures behind the wall. In fact, the new Australian Standard devotes an entire section to drainage design. To tell us about it, consulting engineer Andrew Shirley.
The lack of drainage becomes a problem for a retaining wall because it increases very substantially the loads on the retaining wall, normally by up to twice the load. So that if you designed a wall in the normal manner and then you got hydrostatic forces on the wall, then the loads almost double. Secondly, the many materials forming the soil that you are retaining, when they become soft or wetted, then the soil loses strength, so it is not as strong as it was before. Thirdly, the water lying on the base of the wall and in and around the foundation can cause problems of softening of the actual material on which the retaining wall is sitting, and consequently the wall may slide, it may move, and cause all sorts of problems in terms of that function. And the final issue is that if the drainage are not correctly installed, then parts of the wall can become damp in the lower sections, and these dampness in the lower sections can then cause health problems for people living in houses, the rear wall of which is a retaining wall. I've come across a number of problems with the design details provided by engineers on their various engineering drawings, and this is an example of such a problem. There is no indication whatsoever that there should be any drainage behind the wall, neither is there any indication of any sealing of the back of the wall. The result is that water pressures can build up in the material behind the wall, cause seepage through the wall itself and consequent health problems internally, and additional hydrostatic loads on the wall. A further development of another engineer, and in this one we have the wall itself and the backfill. This time we have what is presumed to be a subsoil pipe surrounded by gravel, but there's no indication as to what the gravel's to be or any indication what the pipe should be. How it would function, I don't know. How it would be built, I don't know. Again, we have a foundation slab with a retaining wall, and we have here a dry wall because the engineer doesn't think that his subsoil drainage system will work too well. Many architects would agree they don't work. But you'll see that it's got backfill. There's no attempt to specify what that backfill is. It could be anything, really. It's just backfill. Further, you'll see that the ag line is specified down here. It's a diameter 90 ag line. Now, that would pose a real problem for most suppliers because I'm not aware of any supplier that can really supply that. They use different sorts of materials to that. And all the water is going to lie on the foundation material upon which the slab rests. So if any blockage occurs in this pipeline, then all the foundation strata here will become softened, thus causing settlement of this corner of the building. The inadequate provision of drainage has resulted in failures of the wall. This failure at Hornsby was caused by a failure to provide proper subsoil drainage behind the concrete block retaining wall. Here is the agricultural or subsoil pipe, and you can see that there is absolutely no free draining backfill at all behind the concrete block retaining wall. The overload of the drainage system was caused by water flowing over the cliff line at the rear, saturating the soil immediately behind the wall, thus leading to overload of the wall and failure. And you can see the remnants of the failed wall in the lower part of this photograph, then caused a large boulder to impinge upon the house, and as a result the house was then demolished. Now let us look at some examples of good drainage design which are included in the standard as an appendix, and these have been included because of the problems that engineers have had, clearly. The first one that I'd like to show you is the one behind a typical cantilever retaining wall sitting on the usual foundation and concrete vertical wall. And the key features of the subsoil drainage system behind the wall is the subsoil drainage pipe itself surrounded by gravel, which is separated from the soil surrounding it by a geotextile, or you could provide weep holes through the retaining wall and thus eliminate the subsoil pipe itself. And there is a geocomposite which is connected to the top of the gravel that goes up behind the wall itself. This geocomposite material is a plastic geocell, we call it, which is a large void, and on one side of it there is a geotextile, which is a blanket type material that prevents the backfill granular fill going into the void. We then have a free draining granular material which can vary widely depending upon the site conditions, and over the top of the free draining material is a compacted seal to prevent the surface water flowing from the area surrounding the retaining wall into the free-draining granular material. You'll notice that the geocomposite, the top of the geocomposite, is protected by a flap of the geotextile going up the back of the wall. And this is to prevent any material going in the top of the void that is formed behind the wall. In some instances, you may not need to provide this geocomposite drain, and in some instances, you may prefer to put this drain on the back excavated surface. But these are all a matter for the designer to consider at the particular time. A further example of the subsoil drainage system behind a retaining wall is this one behind the usual crib block retaining wall. The majority of the features are exactly as I showed you before in the cantilever wall, but in this case, because of the unique way that a crib block wall is built, the foundation slopes backwards to create the effect of the retaining wall in its slope. We therefore must provide for the subsoil drainage to go over the top of the foundation to a free efflux point. This is the reason for the concrete backfill, and if we do not provide a concrete backfill of this type, then water can lie in the base of the excavation and so soften and reduce the strength of the foundation of the retaining wall. In some instances, people have not used concrete backfill and taken subsoil drainage right to the base of the wall. If you did that, you would need to provide a subsoil drain at the base of the wall and probably take very special precautions to seal off the foundation strata so that it would not be weakened or softened by waters lying in the base of the excavation. Free draining gravel backfill is a material used in backfilling behind retaining walls and around subsoil drains that does not have any significant clay or silt materials. And these are normally represented on a particle size distribution graph in which laboratory tests can indicate for you the amount of clay and silt and sand in a particular material. If we look at this grading curve, we find we have the particle size along the bottom going from clay through to cobbles and gravel against the percentage passing each particular sieve or size. And if you'll notice, these materials are all relatively free draining granular materials because they are essentially uniform in their size, although one, termed filling sand, actually has got a range of sizes. But you'll notice there are no fine to medium silt or clay particles. Sometimes you get a little bit of dust on the particles, but those are insignificant. The essential thing is there is no clay or silt. If you have clay or silt, the material becomes impervious, and an example of that is in this particular graph where you can see a wide range of particles, and that makes a material impervious. If we refer, however, to a free draining material, to specify it, we usually do that by saying that the material shall comply with a particular grading curve. A simple test to check on the porosity of a particular granular material that you're proposing to use would be to take a small plastic cup like this, take a sample of the sand or the silty sand or the gravel material you have, fill the cup up, put some water on it, and then create some holes in the cup with a penknife rather than a pencil, and pour water on it and see whether the water flows through. If the water lies on the top of the material, doesn't flow through, it's virtually impervious. It's a very quick, simple thing you can do, and it uses an inexpensive device. One of the problems about assessing permeability is that some people think that having a lot of large holes in a backfill equals a very porous material. And so they specify things like brickbats, which are small pieces of broken brick and tiles and pipes. And they put these behind retaining walls. Because they have large holes, engineers commonly think they are porous. Well, they are for a few years until the silt and the mud washes into all the spaces between the brickbats and broken pieces of pipe, thus clogging it up and becoming clay, so that the the material that started off as being very porous is now completely impervious. So to prevent the movement of silt and clayey materials into these open, free draining materials, commonly today we specify geotextile materials. This is an example of a geotextile material. This is actually called a needle punched felt geotextile. It's a non-woven geotextile and widely used for the installation of drainage systems behind retaining walls. Here is another geotextile also commonly used. It's black as opposed to the one grey, just by different manufacturers. Many engineers specify these products as if there's absolutely no difference between the two products. However, as a geotextile is to allow water to flow through, a simple test by simply pouring water on one geotextile, you can see the water simply runs off it. This geotextile suffers from what we call hydrophobia, that is, that it doesn't want to absorb water readily. Whereas the black material, if we pour water on it, the water is readily absorbed and immediately flows through, and thus providing effective drainage. The grey one, as you can see, is called hydrophobic, whereas the black one is non-hydrophobic. I mentioned before geocomposites, and an example of a geocomposite is this one, where you see the geotextile is surrounding the hollow cell plastic material. This is called drainage cell. There is another type called core drain, and in this one we again have a cell like a honeycomb plastic structure, and a different type of geotextile is placed over it. We then have another variety which is used in different situations. This one's actually for drainage on paving slabs. It's called plaza deck. Again, you see there's the geotextile on top of the hollow open structure. I'd like to draw your attention to the requirement in the standard that a matter that a designer, that includes structural and civil engineers, shall consider is the design of drainage. And you need to present good details, proper details of all your drainage systems, because if you don't, you will find yourself out of step with other engineers.
There have also been innovations in the materials used as backfill in retaining walls. One of these is fly ash, a waste material from coal-fired power stations. At Mount Piper, near Lithgow in New South Wales, some new retaining walls used fly ash as the reinforced backfill, and this was compared with others which used crushed sandstone as the reinforced backfill. Using these two materials in similar sized walls has given us a unique opportunity to compare and monitor the engineering use of fly ash in this way. In this next presentation, we interview design engineer Colin Cartwright from the Reinforced Earth Company.
Part of the upgrading of the Mount Piper power station, they had a requirement for 2 new coal dump hoppers. Now this gave Pacific Power the prime opportunity to test the performance of one of their byproducts, being fly ash, as used as a reinforced earth backfill. So in the southern hopper they used the sandstone backfill, and in the western hopper they used the fly ash backfill.
Now, fly ash is a much lighter material and also much finer material as compared to traditional sandstone backfill. How did this affect the engineering properties that you used in the design?
That's right, Mark. The principle of reinforced earth is that a granular backfill is combined with the steel reinforcing strips to create a homogeneous mass, capable of supporting not only its own loads, self-weight loads, but those of loads applied to it. Now, with a traditional type reinforced earth structure, we would use a granular material. Now, the granular material combined with the steel strips created a frictional structure which performed in accordance with what we expected, or the intent of the design. Now, with the sandstone, the friction angle of the material is in the vicinity of 36 degrees. For the fly ash we were using at Mount Piper, it came up at 31.5 degrees, or in the vicinity there. So it was a lot less than what we would traditionally use, which ultimately meant the length of strips were in the vicinity of 1 to 2 metres longer. Now the other important characteristic that we take into account is the bulk density of the material. Now for a sandstone, the bulk density would be in the order of 20 kilonewtons per cubic metre. For the fly ash, it was somewhere in the order of 14 kilonewtons per cubic metre. What this meant to the design was that the number of strips within the reinforced earth block was reduced. So ultimately we had longer strips but a less number of them, which meant the kilograms of steel per square metre of facing was less than a traditional type structure.
Okay, now this is one of the first major reinforced structure using fly ash. How did you determine those engineering properties during the tendering and the design process?
Well, there's been some work done in the past on the Vales Point fly ash in the Hunter Valley in New South Wales. They were looking at this material as a use. This data was included in the tender documents, and we looked at that to see the feasibility of using it as a reinforced earth fill. Then once Barclay Molam had awarded us the contract to design and supply the components for the structures, we undertook some of our own testing so we could be 100% sure within ourselves that the backfill was going to work. We engaged Longmack and Associates to test both the physical, chemical and electrical qualities of this material. Now, as I've said, the physical properties were either friction angle was less and the bulk density was less, but the real surprise came within the chemical and electrical qualities of the material. We require a pH of in the range of between 5 and 10. We tested the fly ash and the range was around about 4.9 to 5, so it was very close to what our normal allowance was. We made the decision that no further corrosion allowances needed to be taken into account. The electrical and chemical properties of the material, being the resistivity of the material, the chlorides and sulfates of the material, all were within standard ranges that we would use for the design of a traditional type reinforced earth structure.
Okay, so the steel strips in the reinforced earth used with the fly ash backfill was ordinary strips used by the reinforced earth?
It was the same strip that we would use we used in the southern hopper, which had sand steel, and it was the same strip that we'd use on our normal Department of Transport type structure. Yes.
What did the drainage design on the site consist of?
Well, the drainage design was a very important aspect of the design. Fly ash was very reactive with water, and when it became saturated, lost all its frictional characteristics. Therefore, to ensure against any groundwater movement up through the reinforced earth structure, a blanket drain was firstly constructed overlying the existing foundation. That consisted of a sand and gravel and filter cloth barrier, which was laid out entirely under the structure. Then as the earthworks or the placement of fly ash was coming up against the facing, a wick drain was constructed at the back of the structure. Now this wick drain separated the reinforced earth zone and the general fill zone. Now the idea behind the wick drain was to ensure that any water moving from the top of the structure would pass down behind the reinforced earth structure and then out through the blanket drain at the bottom. Now, of course, there was always going to be some movement of small amounts of percolation of water through the reinforced earth structure, and these were designed to be allowed to pass out through the facing. And just at the facing we had a simple filter cloth layer behind the facing which the water could pass through, but while the filter cloth was maintaining the fine fly ash backfill. Now, as a precautionary measure above all the other drainage mechanisms that were in place, a capping layer or an impermeable capping layer was constructed over the top of the reinforced earth structure. Now this comprised of a very densely compacted clay material, and this was then the idea behind this is to intercept any water passing through the coal stockpile would then be directed over and away and around behind the reinforced earth structure.
With the fly ash material backfill, what level of compaction was required and how was compaction achieved in the reinforced earth wall? And where was the water added to the fly ash?
This is a very interesting concept with the use of the fly ash and took a number of people by surprise. We were obtaining it from a stockpile, or the Mount Piper stockpile. We were loading it and conditioning it into trucks and moving that to the workface area, and then it was being dumped and placed and spread with our normal 20-tonne or 30-tonne earthwork excavator as required. Now, generally with earthworks operation, we rolled up there with our 10-tonne and 2-tonne rollers and our whacker plates. But what was found very early on in the process, that just the general movement of the excavator over the fly ash fill, we were achieving compactions well in excess of the specification. The specification had a requirement of 98% standard, and just with general movement of the excavator, we were achieving well in the vicinity of 100 or over % standard compaction, which made it very easy material to work and spread.
Okay. And what initial lean was given to the facing panel units, and was it different? Any different to normal?
Well, one of the easy, good, great concepts with reinforced earth is that no external, apart from the base row, no external propping is required for the reinforced earth facing. So the discrete individual elements are just placed and then move accordingly to the placement and compaction of the backfill. Now, with a traditional type backfill, we generally allow 10 millimetres of layback per 1.5 metre high, 1.5 metres of facing. For the fly ash, I think it varied. Maybe we got up to 20 millimetres in some area, but generally it was still in the same sort of vicinity as we would use for a sandstone. So there was no excessively laying back required, and when the backfill was compacted, the panels were not moving out of the vertical plane that they were designed to be at.
Okay. And what sort of long-term monitoring is being proposed for this?
Well, on the structure, they've installed a number of mechanisms for monitoring. One being that some stress gauges or movement gauges have been placed on the facing. Now, these are going to measure both on the traditional structure and on the fly ash structure, and this is going to measure any movements in the facing while it's in service over the next 10, 20 years or whatever it may be. Then also, we've also placed within the reinforced earth fill, we've placed some sacrificial strips. Now, at some time in the future, someone will come along and extract these strips, and they will be tested for corrosion and frictional characteristics and the like.
Okay, well, thanks very much, Colin.
That's a pleasure, Mark.
This brickwork retaining wall is a common form of retaining wall in domestic type applications. Basically, it's built wider at the base, relying on its mass to withstand earth pressures. However, new structures associated with concrete modular blocks are proving to be very versatile and attractive. As shown in this next video presentation, these structures rely on specialised geotextiles to reinforce the soil.
The first step in constructing the wall is to get the base, the first course, done correctly. By using a granular road base and compacting it well, getting the levels and everything right. Once you lay the first layer of segmental blocks, you've virtually predetermined your levels and the line for the rest of the wall. After that, it's relatively easy. It's just a matter of putting in the fiberglass pins, which help in the actual alignment of the wall, and they retain the geogrid, which goes in predetermined layers depending on the design of the wall. And it's just virtually a means of stacking them on top of each other, line by line, and putting in the layers of compacted backfill as we're going up. Now, the versatility and flexibility of the actual keystone lended itself to this particular application. Also, secondly, it was most cost effective compared to other means of bank stabilisation and retaining walls.
The RTA has examined all kinds of retaining wall options. Reinforced soil walls have advantages in lower cost, ease of construction, the ability to integrate the construction of the wall into the construction program for the site, especially when we're doing roadwork embankment construction. And it's tolerant of foundation conditions. The RTA has utilised steel and synthetics in both strap and grid formations. We used them at Akuna Bay in a foreshore application. Concrete panels have the difficulty of requiring large lifting equipment on site during the erection of all panel segments, whereas the modular blocks have an advantage in that essentially they can be lifted by 1 or 2 people. On the Pacific Highway leading into Gosford, the RTA has constructed an extensive wall system there which follows the road geometry almost precisely.
As we have seen, earth-retaining structures play an important role in our modern built environment, and the new Australian standard will play an important part in standardising our use of these structures. In this program, we have seen the implications of the introduction of the limit state design approach, the importance of drainage design, how new types of fill materials have been used, and examples of modular block reinforced retaining walls. Before we go, we have an excerpt from an American video about a relatively new pavement overlay product called ultra-thin whitetopping. It's been put together by the American Concrete Pavement Association, and we think you might find it interesting.
Allentown officials are paving the way for a new technology in the city. It has to do with the roads and the method the city uses to repair them. There was a demonstration of the technique this morning on Linden Street. Usually when you think of roads, you think of blacktop, but this is something different. City leaders say Allentown is becoming the first in the Northeast to try this new method. It's concrete with a higher cement factor than usual so it dries quicker, and special fibers that are said to absorb impact. It was developed in Tennessee and is being promoted by a group of interested concrete producers.
The concept here is to put down a concrete wear surface that is resistant to rutting and washboarding of the asphalt surfaces.
They're trying this experiment in this area of the city because of the way the roadway is. They say that the roadway here is under a lot of stress, and that's because it's a downgrade leading to a stop sign. They say that the stress here can actually make the blacktop buckle, and they also say that that happens in a lot of other sections of the city.
We get what we call carpeting, the blacktop rolls, and even though we could put more blacktop in over a period of years, you have that recurring. This is a new material that's being developed, and we hope that will stop the carpeting, that we don't have to come back in 4 or 5 years and repave it again.
And because this is an experiment, it will be watched closely. PennDOT leaders were on hand this morning to check out the new method, as was the city's head of streets.
Ultra-thin whitetopping, UTW, the newest and best idea in pavement overlays. The reason why is simple. Ultra-thin whitetopping delivers durability, low initial cost, fast application times, and reduced turnaround times, and the advantages of a concrete pavement, like resistance to rutting and shoving, improved performance over the life of the road, and a cool light reflecting surface. It's the ideal pavement for city streets, local or low volume roads, parking areas, intersections, even general aviation applications such as runways, taxiways, and aprons. Ultra-thin concrete whitetopping is basically pavement rehab. It takes deteriorated asphalt pavement that has sufficient structure but poor or rutted surface and overlays it with 2 to 4 inches of high-strength synthetic fiber-reinforced concrete. Research proves that a bond is formed between the asphalt substructure and the concrete overlay. This bond creates a composite pavement with many of the best characteristics of the toughest pavement material available. Experts say that ultra-thin whitetopping is the most cost-effective way to save an asphalt pavement before it's totally dead. Why? Because using the existing asphalt as a substructure results in maximum resource utilization. And ultra-thin whitetopping does not require the cure times of standard concrete paving. For example, using fast-track paving, this road was ready for use 18 hours after UTW was applied, and less than 24 hours is common. Finally, because it's basically an overlay process, you can mill off the asphalt to the thickness of the whitetopping and complete your resurfacing without changing the surface grade. Here's how a typical ultra-thin whitetopping project progresses. Because of heavy traffic and trucks, this intersection in Nashville, Tennessee was showing signs of severe washboarding and rutting less than a year after asphalt resurfacing. Maintenance costs were out of hand, and drivers complained about the poor surface within months of resurfacing. The city decided to try ultra-thin whitetopping. Milling was begun in preparation for a 3-inch overlay of high-strength synthetic fiber reinforced whitetopping. When milling, they're careful to not mill through the asphalt to the sub-base. UTW requires an asphalt surface to bond to. Cleaning and brooming after milling assures a more complete bond between the old and new surfaces. On this project, concrete placement began less than 4 hours after the project was started. The mix design can be varied to meet the open for traffic requirements of an individual project. Any ready-mix plant can deliver the mix required, using locally available cement, aggregates, and water reducers that produce high strengths while maintaining mix workability. Synthetic fibers added to the mix enhance impact and abrasion resistance and reinforce the joints between the mini slabs. Ultra-thin white-topping mix is placed with conventional paving equipment, fixed or slip form. Even inexpensive vibrating screeds or hand leveling equipment can do the job. Finishing is kept to a minimum. Normally, a highway straight edge followed by brooming or tining are all that's required. Curing begins immediately, before joint sawing. Joints in ultra-thin white topping are cut much closer together than with conventional concrete paving projects. Closer spacing creates a paving block effect that resists bending stress and helps prevent cracking. The mini slabs created by this process are 2 to 6 foot square, depending on the overlay thickness. Early sawing is recommended, just as soon as the surface can tolerate foot traffic. The mini slabs are so compact that joint sealing is not required. Of all the physical characteristics at UTW, the close joint spacing is what most people notice first. The new composite pavement structure provides a smooth, eye-appealing, and highly rut-resistant surface that will perform with minimum maintenance. Just these easy steps: prepare surface, place material, finish and cure, saw joints, and open to traffic are all that's required for a project. But most important of all, it has the longer life characteristics of concrete.
If you'd like more information on that, you might like to call the Australian Concrete Association. Well, that's all for this edition of the Civil Brief. So on behalf of Comprehensive Resources, goodbye.